Since 1984, I was employed as a in structures at Thames Poly. I was there to do a higher degree and then just stayed. And then an ex-colleague from Freeman Fox and Partners, because I worked for Freeman, some fantastic experience at Freeman Fox, but an ex-colleague called Bill Day had, with Brian Boughton and another guy, had set up a business locally to me in Sidcup called SSP, Structural Survey Partnership. I say the MD was Brian Boughton, and I've worked closely with Brian ever since. At SSP, I was given a multi-span masonry bridge over the Thames, Chertsey Bridge, to analyse. Couldn't find out, and nobody had really analysed a bridge like that before. It seemed to be an awful lot of iterative calculations, and I was very much into programming at the time, so I wrote a program, ASARC, and that went on general release. Most bridge authorities bought it, and consultants, but spent 2 years developing it. As soon as I developed it, another program came on the scene called Archie, Bill Harvey's Archie. We did actually, most authorities bought both programs as a check on each other. Bill and I did actually talk about having a joint input data to save people inputting the data twice, but we never actually got round to it. At the end of the 20th century, most bridges have been assessed, and that led to the development of what we call the MAR system. Brian developed the practical side, and I developed the theory. It was a new concept at the time. We had difficulty getting it accepted by traditionalists, but now, 26 years later, we've applied it to over 300 arches in UK, Australia, Asia, etc. So it's been a big success. Sorry. So, masonry arches, everybody seems to like masonry arches. They appear in paintings, they're aesthetically acceptable. A lot of them have never had any maintenance in their life, and they're still standing, durable, tolerant of deformation, built with local labour and local materials. They're part of our heritage. So they must be the ultimate in sustainability. Unlike concrete and steel bridges, they don't require any maintenance, and I think they should be preserved. This is one of the first bridges we strengthened in 1997. You can see the MAR system in the bridge there, and still the same today. No maintenance, hasn't had any work done on it. This is another. We were in Chelmsford fairly recently, and took a picture of this. This is a viaduct that was done in the year 2000 using the MAR system, and again, it hasn't been touched, and it's still as good today as it was when the MAR system was first installed. A little bit of background. The MAR system, as I say, it's been installed for over 26 years now, and we haven't had any problems. But Goldhawk itself was originally allied to Helifix. We started with Helifix as a partner to Helifix, and business was good. But Helifix were taken over. Well, we called ourselves Goldhawk, and we were with Helifix because we had a meeting in the pub in Goldhawk Road, and that led to the name of the company. All best things happen in the pub. Helifix was taken over by a large conglomerate who didn't want to get hands dirty by being involved with contractors, so Goldhawk had to find another partner. Helifix recommended 4 of the best approved contractors for us to interview. Stress UK came along first, and we hit it off well with the MD, Dave Kitching. So we didn't bother with the others, and we've been partners with Stress UK ever since 2012, and it's all worked well. So that's a little bit of background to the company, if you like, and me. If we get to masonry bridges, we can see one being constructed that's actually being reconstructed, to be honest. But you can see the, hang on, I'll get a pointer. You can see the centering on the bridge. So you build the arch over the centering and remove the centering, and the arch falls down a bit and goes into compression. In this case, they built spandrels as well as the arch barrel, which is a bit unusual because normally you build the arch barrel first and then build the spandrels over. So you build your centering, then you build your arch over. Normally it's layers of bricks at a time. You remove your centering and the arch falls. And that puts compression into each ring, and because each ring is actually a different profile, different length, it's got different stiffness, you could actually get ring separation between the rings even on the day the bridge was built. Then after that happens, then you put the fill over, that increases the compression in the barrel and build your spandrel walls. So when the centering is removed, each ring goes into compression, but that only works for what we call roll-up construction, which is shown there. Bonded construction is slightly different, and that behaves slightly differently. Stone barrels, or ashlar or whatever, they behave, again, they don't exhibit ring separation the same. Random rubble barrels are a different kettle of fish altogether. So the assessment codes treat all types of construction the same, and I do think a bit more research needs to be done on how the different responses of the different types of barrel. A lot of academics will tell you that, try to tell you anyway, that masonry arch bridges are 3D structures. It should be analysed as such, but they actually rarely act as 3D structures. They comprise elements that tend to act against each other. You've got your spandrel parapet walls, they've got a stiff vertical plane, but they lack stiffness in the lateral plane. The barrel itself there acts like a jelly mold in the horizontal plane as loads go over it, and in 90% of the cases we see a crack going around the barrel, and it will depend on if the spandrels have been thickened as they go down, the position of the crack. 90% of the time we see that. The fill and the traffic loading provide horizontal lateral thrust against the spandrel walls, and you get cases where these push out under the wall. So it's the sort of competing elements in the same structure. And that's, 90% of the time we see these cracks. This is a bridge we're doing in India at the moment, in the Gondal region, Sarda Bridge, and you can see it's a beautiful bridge, but the parapet walls have got no real stiffness in them and very low spandrel walls, and this arch is fairly flexible. It moves up and down, so there's only lightweight traffic uses the bridge at the moment. And so the spandrels can move with the barrel, so you don't get cracking in the barrel as normal. But that's sort of fairly unusual. This is the mast system. We stick that into the underside of the bridge. We don't need to work from the top of the bridge or close the road or anything like that. We stick the mast system into the underside of the bridge. What it looks like as an installation. But the circumferential bars around the barrel, they strengthen the barrel, and then the transverse bars, they hold the parapet and the spandrel walls together, so they're effectively in tension. We tend to have a barrel at right angles to, a bar at right angles just to stop overturning of the parapet, sort of belt and braces sort of thing. So that's the mast system as it looks. I should say at this point that I just don't believe in inserting steel bars into masonry. the Mars system isn't really like that. This is supposed to be a solution to ring separation. I sometimes wonder about ring separation because, again, I've had experience of where you sort of bang the soffit with a metal hammer. Some people will say, oh yeah, there's ring separation there. Other people say, no, I don't think so. So, you know, it's a bit of a black art, I think, finding out where the ring separation is. But masonry arches, as the masonry moves, you get micro cracking around large bars. And in this case, some of them were dropping out. Don't prevent cracking in any shape or form. So they still allow cracking to take place. And it's just not a good detail at all, as far as I can see. This is a bridge that we've been asked to strengthen. So there's another case where large diameter bars have been put into masonry, and again, in this case, all it's done is exacerbated other cracks. It's very difficult to drill them all the way through the barrel accurately, but in this case, that's what it needed. So these bars really have made the situation worse, if you like. We only use 6mm bars. In fact, using heli bars, the diameter effectively is only about 4mm. So they've still got that flexibility that you need in masonry bridges. And we put them in what we call Marflex, which always remains flexible, slightly flexible. Some cases we use 8mm bars. I'll come to that later, but I think that's the maximum you can use in a masonry bridge. For skew arches, we angle the transverse bars to be along the line of principal stress, but skew arches try to span perpendicularly between abutments, so you get planes of weakness. So there's a plane of weakness there and a plane of weakness there. So we bridge that plane of weakness, and whole barrel can dig in place. This is a case where bridge has failed along its plane of weakness. A skew bridge failed along the plane of weakness, which is not good. So get to the theory of how the Mars system works. This is a transport research laboratory tested a number of redundant masonry bridges, and they give a quantitative illustration of how masonry bridges perform. As opposed to laboratory models, I'm not a great believer in laboratory models, to be honest. And this one shows the common 4-hinge method of failure. There's a hinge there, etc. There's another one that's done around a sort of rubble bridge, and rubble bridges tend to fail as compression failure. And so there's the two different types of failure really for masonry bridges. I've built a number of finite element models. The package in the university was only elastic, so build the model, take away the elements that were overstressed, and then rerun it again until we got equilibrium. But I've done well over 100 finite element models, and that just shows you where the hinges are going to occur in that. But there you are. That's we get to the Mars system. How does that work? We have an arch barrel. We increase the load. You get a hinge forming usually under the load. Then as you increase the load even further, you get another hinge occurring at D. Then as you increase the load even further, you get a hinge acting at B. And then as you increase the load even further, you get 4 hinges, the arch collapses. So it's 4-hinge mechanism collapse. So what we do is we strengthen the arch barrel at C, say, put reinforcement in there, that stops that hinge occurring. So if you stop that hinge occurring, you stop this hinge at D occurring, you stop the hinge at B occurring, you stop the hinge at A occurring. So, I mean, you'll never stop them completely, because this will still always fail, but at a much higher load. So, and that's how the Mars system works. we we delay the hinge at sea, require a higher load to form the hinge at sea, and then the other hinges don't form and the mast system works. The only problem is we don't know where these hinges are going to occur. It depends on the direction of the load, depends on profile, etc., etc. You can only work it out by calculation. So what we do is we put reinforcement in around the whole of the barrel and to cover any position for this hinge at sea. Problem is, if we just put in bars in the bottom ring, we strengthen the bottom ring compared to the other rings, and stiffer ring will attract all the load, and in some cases you can actually weaken the bridge just by putting in a single ring, because the bottom ring might buckle under the increasing thrust. So we put in our radial pins, and that ties all the rings in together, and it also ties the reinforcement, the circumferential reinforcement, to the barrel. The rings don't penetrate the barrel, so any services in the road or anything like that is not affected, so we can work from underneath the barrel. I normally, well, that's the cross section of a typical installation. Heli bars, radial pins. These are the circumferential bars. This is a transverse bar, and the Marflex, it's been developed especially for us. It's amazing stuff. It sticks to anything. In load tests that we've done, it's the brickwork around the Marflex that fails. The bond doesn't fail. So it can be applied in damp conditions, dry conditions, etc. It still works exactly the same. It's a derivative of material that's been used in for 100 years in bridge expansion joints. So it's salt proof, and that's important because stainless steel is affected by salt. The chromium oxide layer of the stainless steel is affected by salt, and you could get rusting if you expose the stainless steel to the salt water that percolates through road bridges from road salts, etc. So that's how the mast system works. The ASARC program, and the Masters program is based on the ASARC program, exactly the same, tested by ARP independently, and found that of all the methods, all the programs that were available, it was the most accurate, best fit to the test data of any of the methods used. And the test data was the actual bridges that were tested by TRL. And this is a test that we did at TRL. It was an independent test carried out at the Transport Research Laboratory, 5-meter span arch, 3 rings, and they put sand between the rings to simulate ring separation. And this was the test at failure. This was the mast system in the bridge, and this was the failure test. The unreinforced bridge took, with ring separation, took 200 kilonewtons. I worked out using MASTIS that it would take 190, and that would give us 7.5, equivalent to a 7.5 ton weight restriction for a bridge like that, a 5-meter span bridge. What we did for the test, they tested the unreinforced bar to destruction, but they didn't test it to failure. They tested it to maximum load. So we jacked it back up into shape, put in just a layer in the outer barrel, in the outer ring, sorry, with just surface steel only, and we got an increase in strength of about 30-odd%. That was just to see what the one ring of reinforcement would do. Then rebuilt the bridge and put in the full mast system, I predicted we had an audience of 60 bridge engineers at Transport Research Laboratory, making sure that there's no fiddling or anything. And I sat down on my laptop using MARSYS, and I predicted it would fail at 349 kilonewtons. I designed enough reinforcement to take it up to 40 tons. We could have put in more reinforcement, got higher failure loads, but we wanted to see how accurate the software was. The barrel actually failed at 345 kilonewtons because the deflection was greater than the jack could cope with, so they had to take the load off, extend the jack, and then load it again, which weakened it a little bit. So I think the 349, we were very pleased with the accuracy of the MARSYS. The MARS system increases the strength of the barrel, takes it up to there. This was where the jack was changed. Retains the flexibility of the barrel, which is very important in masonry arch bridges. We improve the structural response, but we don't change it, and which I think is very important for the performance of masonry bridges. This is me looking my usual miserable self. All the students at the university, all my master's students, were given a dissertation on masonry bridges, and there's no shortage of them coming forwards to do this. And we had a rig in the lab, glass sides, so we could plot the original arch and then plot how it was deforming. So we looked at various forms of construction, various types of fill, etc., etc., saying I don't really believe that laboratory models can accurately represent 100-year-old bridges, but they're useful in comparing different properties and improving what works and what doesn't work. So that's a bit more experience of masonry bridges. We've tested masonry bridges, we've tested lots of bridges with weighbridge testing vehicles. We used to use these, we don't do it now so much, but have cast iron weights on the back, and you know exactly what the wheel load or the axle load is on the vehicle. So we can go from tear up to, say, 25% greater than the design load using these vehicles. And we use vibrating wire gauges, and this was really just to look at dispersion and see what effective width was. And it was actually, it showed that the codes actually were pretty good. The MARS system was demonstrated on the One Show in 2010. Dick Strawbridge came down to a job that we were doing, and it was actually performed by the engineer for Gloucestershire. She recommended it to the BBC, and he came down and demonstrated it for television. So it's our claim to fame. That's us standing. This is me. I'm the good-looking one on Dick's left. So we get to case studies. This is one I did in Sheffield, 2017. It was built in three different sections. There's the original section, then it was extended either side, widen the sections. And they were going to knock it down, put a concrete monstrosity in its place, which is not environmentally friendly or anything like that. So the locals were up in arms about this. They wanted to keep the bridge. So we were then called in to preserve the bridge. When we got there, the contractor had taken the fill off the bridge. So that's what it looked like. Three sections. There's a middle section, the original section, and the extensions. And you can see how rough the outside, I mean the inside, the intrados of the bridge was nice and neat, etc. But the extrados is rough. And you can see if you wanted to core the barrel to find out the thickness, if you take a core through there, through the bit that sticks out, you get a completely different value to if you take a core through the bit that doesn't stick out. So so you get two different thicknesses. So with stone barrels, you need to be very careful when you're taking cores. Very often, I think you should never take the thickness at the elevation as the thickness of the barrel, because very often they either thickened them at the elevation and didn't put as much material in the actual barrel that's carrying the road, or they tried to make it look more elegant and make it thicker on the road. But very often in like rubble bridges, the elevation actually can give you a better idea of the thickness of the barrel than what you get by coring. But anyway, the backing on this bridge seemed pretty good condition, which is, not always the case. I don't think you can rely on backing, because very often it moves away from the back of the barrel, and you get ratcheting effect, and it doesn't become as effective as it was when it was originally built. So you need to be quite careful when you're taking backing into account. And this is, I think, a big no-no. You never put a concrete slab over a bridge. We've had cases, we remember one bridge in London where a slab had been put over the bridge and was acting as a seesaw. So the wheel came on one side, the other side came up, etc. A bit daft. In this case, this is concentrating, instead of having an axle load there and an axle load there, separate axle load there, etc. It's concentrating the whole bogie load at the crown of the arch, or there's no dispersion down from the arch from the arch barrel from the slab. So there's no dispersion away. So it's concentrating the load on the slab, and always seems to be a bit of a daft idea to me. But anyway, that's the slabs. This is, you can see the other side. The fill is completely different. It's just a load of rocks, etc. And so, fill it's always difficult to predict the properties of fill. Anyway, we installed the system. This is us positioning our floating pontoons for our work platform. The flow in the river was controlled by a dam, and so we were quite confident in using floating, but very often we put in just a scaffold poles and a platform on top. Approximate cost for this one was 130 to 150,000 pounds, but the mast system itself was 70,000 pounds. Took about 6 to 7 weeks for our team, and that included setup and demobilization. So this is the platform in place. This is our access to the bridge. So you can see it's fairly sophisticated, and that's the working platform. And that's the slots being cut to put the mast system in. The Marflex isn't in place, but the bars seem to be in place there. And that's the mast system in place. So you can see, it's very difficult to actually see what we've done. Make it a neat job. I'm not a believer in taking the bars between different sections, because they've got different stiffnesses, they behave differently, and I like to maintain the original response of the bridge to allow it to move in the way it was originally built. This section doesn't need strengthening, so the end section didn't need strengthening. So this is the mast system in the bridge. We didn't need to put it in that section. The middle section was the section that needed the most reinforcement, and we only put in nominal reinforcement. This is a nominal system there. It's just one bar transversely and one bar circumferentially at 450 centres. So that's our system in that bridge. This is another bridge in South Wales. It suffered from serious flood damage. It was buckled, poor state. So we pushed, as we did in the laboratory for our test bridge, we pushed the barrel back to maintain its profile. And in order to do that, we had to excavate, which is not really a good idea, but we had to excavate over the barrel. I found a big lump of concrete in there, which was causing the bulge in the barrel. So you never know what you're going to find. You get old pipes, you get boots, you get all sorts of things in the fill, sometimes used as skips, I think, when they were open. And that's the system put in the bridge. It's a way out in the country. It doesn't look very nice. It's not pretty, but it preserved the bridge, which was good. This is another case in the middle of Birmingham that we did. It was a bridge that was in 3 sections. You can't see the end section, but the middle section was a masonry bridge and the outer section was a masonry bridge, all in line because a big wide street. Middle section had been strengthened before we got there by putting in this arch underneath. In order to do that, I had to build new foundations, reduce the width of the canal, etc. And it was expensive, I would think. So we came along because they were putting in the metro over this section of the bridge, and we put in the MAR system, and this is what the MAR system looked like. So it didn't need to affect anybody above the bridge, didn't reduce the width of the canal, and etc. And I've had a friend who's actually been through there twice in a narrow boat. I've said, can you take a picture of our installation? And he's missed it. He remembered this bit, but he didn't notice the mast system. It's an unusual bridge in that had that sort of profile. We proved that by digging trenches across the top of the bridge. So we show these bits here. So the hinges occurred there, and there for loading, and we designed the mast system as such. There's another bridge that Brunel designed or built, I don't know. It's near Reading on the Great Western Railway, called Briscoe's Bridge, constructed just before he died. So I can say I've designed something that's improved on Brunel's work, so feather in my little cap. But this is the bridge. This was Brunel's drawing, and there's not very much backing, even though it's a pseudo-elliptical arch. Not much in the way of backing. And what happens here is that the embankment slips, so it settles. So any backing behind an arch like that actually falls away from the arch. And we can see that in my local station at Bexley. There's a tunnel goes under the platform there, and you can see how it's settled on the side of the platform. I seem to remember that's been renewed for a while. So this is moved since I've moved into this area, although I've been in this area for 50 odd years. Anyway, this was the bridge, just carried a trackway underneath, people walking dogs, etc. mainly. This I always find it's a good idea to just have a pole, stick it under the bridge when something's going over the top, and it gives you a feeling for the response of the bridge, gives you a feel for the bridge of doing that. I didn't realise I was quite so bold, to be honest, until I saw that picture, but which is a bit of a shock. But the aggregate trains going over this, you got 10mm deflection. They were huge trains, and bits were dropping out, and it was quite frightening standing underneath this bridge, watching it go up and down. And as each bogie went over, it was acted perfectly elastically. It went down 10mm, back up, down 10mm, back up as the train moved slowly over the bridge. So it was a very interesting exercise. The bridge wasn't actually elliptical, it was 3-centered, which are quite common because it's a lot easier to set out a 3-centered arch. You got a circle there, and then a circle between them. And so we designed a system. So we replaced the backing by putting in, because our sister company Stress do a reforce system, which is for reinforcing foundations, and so that pumps out a very controlled amount of material, because we could not afford to let any of the grout go into the ballast that was supporting the railway line, because they have to keep reballasting, etc. So we couldn't affect the ballast. So this gave us a very controlled flow. We knew exactly what we were putting and exactly where we were putting it, and that gave us improved the backing to the arch, to the barrel. We then inserted our MAR system. Now, propping, normally we don't have propping. Normally we just, because I design the temporary condition, I check the strength of the arch for the slots being cut, and if it doesn't, because they're only very small slots, 12 mil by, say, transverse slots of 26 mil deep, it's just like a big loss of mortar. So I normally check that to make sure the bridge doesn't need a weight restriction, or doesn't reduce significantly in capacity, to make it unsafe for us to work there. But on this bridge, I think we were quite we worked with Arcadis, and they designed the props for us, and the soft propping, because we don't want hard spots. So that's a rubber pad, 25 mil deep rubber pad, and so we work between the props. And I think because of the amount of deflection of the bridge as the train was going over, it was 11 o'clock every morning when these trains went over, we were quite grateful for the props, to be honest, but we don't normally recommend them. But in this case, we used 8mm bars that we get from Helifix, 8mm bars around the barrel to try and improve the stiffness. And that's the cross section of the railway line. So 8mm bars in our wonderful Marflex material, which again remains relatively flexible. So we, when the props were put in, it reduced the deflection from 10 mil to 6 mil, so that was the effect of the props. In the backing into the arch again, replacing the backing, which had fallen away, reduced the deflection to 3.5 mil, which shows you the effect of that. Then putting in our MAR system, you can see that's the engine going over, and this is the wagons, reduced the deflection to 1.25mm. I think I'd calculated it should be 2.
Halo?
Sorry?
Teraz słyszę, dzień dobry.
Sorry? Can't hear? Anyway, so I'd calculated that it was going to be about 2 millimeters or something, but so we achieved what we wanted to in the bridge using the system. This is a system in the bridge, and so it gives people confidence that we've strengthened the bridge. It doesn't deflect as much, and it looks. So the arch was upgraded from RA5 to RA10, completed the job on time, and they didn't have to close the railway line or anything, because the alternative was to rebuild this bridge, which would have meant closing a very busy railway line, and etc. And we refurbished the brickwork, redid the brickwork, etc. So the bridge is back to normal. Another job we're working on at the moment, we're actually installing our system as we speak. This is in Cardiff. Again, working with Arcadis and Amy and Hamco Griffin, same people, but Transport for Wales in this case. The barrel of the bridge was 700 mil thick. It had a brick layer over the top, so obviously it had all been taken away and the brick layers put in, and lean mixed concrete put in under the ballast, or the ballast put over, I should say. The original assessment took the full this width of the bridge, 960 millimeters, I think it was, which was not correct, because as we've seen earlier, when you remove the centering, the barrel sinks and it all goes into compression. The brick layer hasn't had a chance to sink because it's been built over the barrel, so there's no compression in that brick layer. So it's not actually doing anything. So I don't know why I put in there in the first place. The lean mix was all cracking up because there was water pouring through the barrel. So the lean mix was cracking up, not really being much use whatsoever. So we put our Mars system in the barrel, again using 8 millimeter bars to improve the stiffness, and so that's the system. We've had to recase. I'm just not a fan of recasing masonry bridges because, again, you're putting bricks in that have no stress in them, and but we've had to recase some of it, so we're anchoring our bars in there. So because you can't anchor it in bricks that don't have any stress in them, and that's what it looks like. Again, they've designed propping for us, but normally, in this case, I don't think we need it, to be honest, because it's fairly lightweight loading. Although after we designed the Mars system, Transport for Wales came along and said, actually, we want RA8 because we've got tamper vehicles going over this. So if the tamper vehicles were going at 5 miles an hour, then we calculated that it could take them. And they were RA8 levels, but we had to upgrade it to RA6, which was good. We don't know what the original, I think it was RA0 actually, we got to in the end because it was overestimated in the first place. Another thing, please don't do. There's a lot of standard network rail standard details that I don't agree with, but this is the natural crack that goes around the spandrel walls, and these people wanted to stitch it, and all that will do is move the crack from there to there eventually, and it won't do any good whatsoever. So there's a number of network rail standard details that I have issue with, I must admit. So please don't do that. I think when you're designing a repair for, well, any structure really, you need to work out the cause of the damage first, what's causing the cracks, etc., before you start thinking about repairs. This is another beautiful bridge that we did. This is over the River Nene in Oundle in Northamptonshire. First records in 14th century, and then it was destroyed by floods, rebuilt, etc., rebuilt, widened, etc. So in that case, we've got lots of different foundation types, lots of different arch types, etc. It comprises 13 spans from 3.5 meters to 6.2 meters, and they wanted a weight restriction from 3 tons to 44 tons and SV 100 vehicles. So we come on site, but in the January 2000, there's massive floods. So the whole site was flooded out. You can see the bridge there. There's a backwater goes up the side of the bridge and completely flooded. This was taken by one of our guys in an airplane flying over. As soon as the floods go and we were able to start working, COVID comes along. And so we still carried on working. We had very strict site rules. We had air-fed helmets for each of our operatives, and they worked alone. All site rules were really strict. Only one person in the canteen at a time. Everybody had to have their own cutlery, and everything was kept separate, and everybody had to have their own cars to get to site, etc. But we did it, and got the job done. All these different forms of construction, over the different widths of the bridge. This was Gothic construction, and but fortunately that was the strongest part of the bridge, the oldest part of the bridge and the strongest part of the bridge, and we didn't have to touch it, which I was quite pleased with. And this is us having finished the bridge. That's our system in place. So you can just, it's not a very good slide this, but you can see we have separate different forms of construction for the different parts of the bridge. When you're upgrading from 3 tons, was it 3 tons to 40 tons? I can't remember now, but you need to be aware of the increase in foundation pressures and all the different foundations. There's foundations, middle of the bridge, south side of the bridge, etc. And we reckon if you, because the foundations have been in place for 100 years and they've consolidated the ground underneath, and we reckon you can increase the foundation by 15%, say, and there's no problem. In this case, we had 21% was the one of the foundation increases. So we recommend that in for principal inspections, you do just have a look at the pier just to see if there's any movement. So that's the bridge. You can see, I think the mast system looks really good in there. We can colour the Marflex to suit the colour of the brickwork, etc. And repaired a lot of the stonework as well. Our guys have done a brilliant job, I think, on that bridge. That's the system in place again, and again it's brand new, so it's very shiny, etc. But that's our system. This is another bridge we did, Thrapston Bridge, again over the River Nene, same people. Another absolutely fabulous bridge. Love to look at it. And it dates back to the 13th century, and it started off with 24 spans. Now there's only 9 spans, range from 5 meters to 9 meters, and they wanted it to go. It had a 7.5 ton weight restriction, single lane working, and again they wanted it to 44 tons plus SV80. This is a video. One of our guys is a drone expert, and this is the site compound, and this is the bridge over there, and the video will play as I'm speaking. But the main problem with this one was the navigation span. Huge amount, large deflection in the middle, deformation in the middle, and it was coming out at here. So didn't seem to be anything wrong with the foundations. We normally core to see what the backing's like in arch barrels, but this one, it looked as though a hinge was forming. So what we did was we closed the bridge while we were doing this arch, but we kept the bridge open for the other ones. Our guys, we've got fantastic craftsmen for detailing brickwork and bringing the brickwork back to what it looked like originally. Lots of cracks in there. But you can see we worked on this. We closed the bridge for this span, and we worked from a floating pontoon. You can just about see the pontoon there. So it's working from a floating pontoon, so that if any barges came past, because it was navigable river, we could actually get out of the way, let them through, etc. But I think we opened up one of the other spans for barges. And again, some of the spans didn't need strengthening, but they were worried about ring separation again. So we calculated the number of pins that we needed to prevent ring separation, because our program gives us the thrust in each of the rings, and we can calculate the difference in thrust and put in shear pins to sufficient shear pins to take that difference. If the full mast system is put in, then we put in shear reinforcement on radial pins at each intersection, and that's always sufficient for stop any ring separation. You can see from the video that we're working there. I don't know if I can. I was hoping to fast forward it, but I can't. But anyway, that's the working under the bridge. Of all these large bridges that we work on, I like working on these little ones just as much. This was a little bridge in Calderdale that had been strengthened by just putting a concrete underneath on wrought iron beams, and it was in a terrible state, as you can see. So the bridge had been had this support added, and it also the abutments had been new abutments had been added under the arch here. So you can see there's a huge restriction to floodwater, etc., and it was in a bit of a state. So the idea was to cut away this, but we didn't want to remove these because that would just be too much. So the way we looked at the arch, there's the inserted abutment here, and as the barrel deflected, it would come away from the abutment here, and you'd get a pivot point here. So so we designed a system where we anchored the barrel to the back of the abutment, took our mast system around the abutment, and made it all as one, if you see what I mean. And so that's the state of the barrel before we started. It was in a very poor state. You can see a 40mm displacement between the stones, and this was the wrought iron tray that was holding the concrete, and you can see why that was put in there, because it was in a terrible state, and the wrought iron was actually corroding, so it was about to fall down anyway. And there's a big heavy plant just next to the bridge which was using it. So our guys worked their magic, and this is the end result. You can see the mast system in place, huge aperture now for floodwater to get through, and they jacked, because there wasn't much fill over the top of this bridge, they jacked all the stones back up into place, and it's back to normal again, this bridge. So I thought that was a great success for us. Now the design process, as I'm the design guy for the mast system, design process, we get an order normally, then we usually get a few drawings of the bridge, we get previous assessments if possible, and normally we go out and monitor mark up the defects for ourselves and check dimensions, etc. I need lots and lots of photographs because very often I don't get to the bridge. You can see this one, I don't know if you can see it, but this is bonded construction, this barrel. And the other side is roll-up construction, which is bricks on edge. And so the barrel had been widened, and so lots of pictures of defects, etc. I put in heli bars in there between the sections, which I don't believe in. And it's always good to have a photo of the traffic use to see what sort of traffic, and you can see that you can get some fairly big lorries on this bridge. So it was all useful information. The design process is that we need technical approval first, so we come up with an AIP, an approval in principle form, and that gets approved by the technical authority. Sometimes they come back to us with queries, and then we have to answer the queries, because it's just deciding on what materials, what dimensions to use, and agreeing that between all of us. Then design to 454 and 458. 454 is for normal ALL assessment live loading, and special vehicles loading is 458. And public roads are supposed to take minimum of SV80 vehicles, so we have to design for that for most public roads. We also use CD 376, which is a design code for unreinforced masonry bridges. It's not strictly relevant to us, but there's an awful lot. There is a lot of good information in there that we tend to use, such as you shouldn't use LM loading, which is given in the Eurocodes for masonry arches. So we designed to these codes and then designed the reinforcement to Eurocode 6, because I think that's about the only design code for reinforcement these days. That's rules reinforced masonry in structures, and I then come up with a design report that goes for approval, and then we agree costs, agree site layout, etc., and go on. So I use the ASAP program to analyze the bridge for pre-design. That gives, profiles, etc., of the arch. Then I use MarSys to work out the moment of resistance that we need, and then design the reinforcement to the Eurocode. Now, in this particular bridge, it was in 2 halves, so you have to be very careful about your effective width and careful about your loading. So, such as this half could actually take authorized weight vehicles, but if you put it up against the edge of the slab, then your effective width really, because the vehicle's got to be in the middle of your effective width is that length there. It's not as in the code. With SV vehicles, again, the effective width, again, they just fit on the slab, and again, your effective width, combined effective width, I should say, is that amount. But then when you load the other slab, you can't get a vehicle on that slab, so one of the wheels has to go on this slab, and really the wheel has to be in the middle of the effective width. So your effective width really is only the width, the dispersed width of the wheel. And same with SV vehicles, out of sequence. Again, the effective width for that, you can take, was it 2L or something, as extra width. And so the effective width there is 2 meters in this case. The vehicle is straddling one and the other, then that's the loading on this slab, and again the effective width is really just width gives you the intensity of loading that we need to design for. You can see there's lots of services in this bridge, but our MAR system doesn't affect services. So we designed our MAR system for each half of the bridge. From that loading, you can see there's different spacing of the bars, etc., but we don't affect the services that go over the bridge. Another bridge that we did in Wales that was strengthened using Armco and concrete over, and lots and lots of flooding at the time. All the local ship shop was flooded out. So we took all that away, put it in our MAR system, and we haven't had any reports of flooding ever since. This is a bridge that we thought was in Turkey, but it was actually in North Iran. It's supposed to be the biggest bridge in the world. We didn't install the system. We trained the guys in this country. It was a UK contractor. So this is the system in place in Iran. And they looked at different options for strengthening the bridge, and the MAR system came out best. And they didn't actually look at technical considerations, historical, etc. They didn't look at the environment. And the big thing about the MAR system is it's environmentally friendly. But this bridge has been studied by academics since the MAR system has been put in, and it's been found that the response, it really helps the bridge against seismic activity, etc. And to show the environmental aspects of the MAR system, I'm nearly finished. Looking at this horrendous practice of infilling masonry bridges, which I think is shocking. In order to infill, you've got to quarry the material. You're going to have massive lorries coming through country lanes, dumping the material. You've got plant on site to distribute the material, and then you're using concrete, which is not environmentally friendly anyway, and you're destroying the biodiversity under the bridge, etc. Use the MAR system. Well, our Marflex is manufactured in Tyne and Wear. Elibar is manufactured in North Wales, and we're in London, and our guys tend to come from the Midlands. We only use small vans, so there's no great big lorries being transported. We use hand tools that we can hire from local hire shops, so we're improving their business. Just need a simple platform or whatever, which we get from the local scaffolder, and we don't need to. The big thing against strengthening bridges is having to close the bridge and traffic diversions, and that uses up loads of energy, etc. So we don't know. Sometimes we have to restrict the width of lorries. We can put in barriers just to restrict the width, but very rarely. So there's no traffic restrictions, and that's what it looks like, and gives people confidence that it's been strengthened, looks good, etc. So that's our MAR system in place. This is the bridge, the infill in the bridge. They put grass over the concrete, but you still got a void under the bridge, which you can't get to inspect, and so that can deteriorate, and you could end up with a big hole in the road. Whereas and that was the original bridge. It was a beautiful bridge. So installing the infill was reportedly 123k. The MAR system comes with everything taken into place. I don't know how much that includes. Our total will be, 86,000 to put it in, and but there's been such an outcry against it, they've had to remove it, and the cost of removing is 400k. So, a bit of a waste of money. So, in conclusion, the MAR system won Millennium Award for Innovation. It was displayed on the Spiral of Innovation at the Millennium Dome, which is not there anymore, which is a shame, but it was displayed as the very best in British ingenuity. And Brian and I had to go up to meet Tony Blair to be presented with a Millennium Award up at the Dome, which was an experience, and it's designed using our in-house, well-proven in-house software. It's the best fit to test data of any of the methods used. It doesn't add weight to the structure, doesn't reduce elevational area for flooding, etc. Doesn't significantly alter the appearance of the structure, it makes it better, and doesn't require a road closure or inconvenience the travelling public. So further advantages, we utilise the inherent strength of the barrel, so we only add minimum material. If you're putting in, saddling or whatever, you're actually adding a lot more extra material. So we use minimum material, which is good for the environment, preserves the flexibility of masonry arches, and slightly improves the structural behaviour and elastic response. Alterations to start, you can hardly see this, but there's lots of services in there, and the barrel is the thick shaded line underneath. That was on one of the busiest junctions in the UK, and we didn't have to have any road closures. We put the MAR system in. So there's alterations to statutory undertakings, etc., not required. Preserves biodiversity because they can swim around our scaffold poles, etc., in the river, etc. Then any other practical alternatives, and any other alternatives. Easily inspected and repaired, although we don't have to do that, but it's easily inspected. Cures, prevents ring separation, which some academics say is the principal mode of failure under cyclic loading of masonry bridges, but yet to be convinced. But anyway, it does that. No road or rail closures required. Inert, durable materials, because the Marflex is all inert materials that last for years. And operations can be planned sequentially. This was a railway bridge. We only had a few hours on a Saturday night, each Saturday night. I think it took about 10 weeks, I can't remember, and Brian knows more. but we put it on a platform, and scaffold platform worked from that. And then at the end of the working period, we just stored it at the side of the bridge, continue to use the bridge, and come back next Saturday night and carry on working. So we can plan operations sequentially, and is the most environmentally friendly method of masonry arch rehabilitation. Dave Kitching will be doing the part 2 of this on the 26th of June, and he'll be talking about the practical aspects of our MARS system. There's also a few YouTube videos, presentations, which I've done, explaining the MARS system, which you obviously can look at. But anyway, thank you for listening, and that's me finished. Quarter of an hour.
Bob,
Yep.
there's during the course of your talk, several questions flashed onto the screen.
Yeah,
We had one from Gordon about the is the road, can the road remain open, which I think you've answered. We had one from Melissa about the propping, is that required and when? And we had one from Helen about the lifespan of the system.
Well, the lifespan.
There were others, but I didn't manage to get them recorded down.
Yeah, well, we've only used the propping on those 2 rail bridges, and I don't think we needed it on the second one. The first one, we didn't actually need it, but it was nice to have it, if you see what I mean. But road bridges and things like that, we've never used propping. We used inert materials, stainless steel, which is protected against the environment, so it should last the lifetime of the bridge. So I reckon 120 years is not a problem. Say we've looked at ones that are 20 odd years old and no deterioration whatsoever. So there's no reason why it can't last for forever, I think. But I'm biased.
There were other questions. Perhaps any those people, if they're still here, would like to ask them.
Well, they're sound asleep.
I have a question. I guess a lot of the arch bridges that you've shown have fairly large stone or masonry used. Is this effective for rubble course arch bridges? Any issues if your stones are kind of small?
Yeah, we'd have to look at the bridge. Each bridge is different. We'd have to look at the bridge. We've used it on rubble bridges without any problems whatsoever. In fact, I think we're doing one at the moment, a rubble bridge. So, yeah, it should actually help the rubble bridge because it will tie the stones into the mortar, etc. So yeah, it should be just as effective in rubble bridges as other bridges.
Okay, thank you.
Hello, Adel Mahmoud from Amy. I got a question basically. If you have a basically transverse crack in the arch in the barrel, do you think the combination of stitching and MAR system will be better than just MAR system? Because
stitching does well. The MAR system.
Because if you don't repair the crack first, then the MAR system wouldn't be off because you still have the barrel is disconnected in a way.
Yeah, well, the transverse bars will bridge the crack, and tie them together so it prevent the crack moving apart. And we designed the transverse reinforcement to give you the same strength as the original barrel, if you see what I mean.
What will be the spacing of the transverse bars? And the diameter is only 6 to 8 millimeters. Is that sufficient to basically? Yeah,
because we still want to allow movement. We want to allow the natural movement of the bridge, and we don't want to put in too thick bars. The crack is, the bars are strong in tension. That we can shear, but We have used stitching in combination with the Mars system, but it's not something that I'm very comfortable with, if you see what I mean. This was really for a bridge with bomb damage that we looked at. Yeah, I think the Mars system will bridge the cracks sufficiently.
In many situations when we had, for example, like tunnels, something like that. So you use the method of stitching, and it seems to have worked. Yeah, so it is, I don't know.
Have you gone back?
Say that the position of the shift of the cracks in different places. So
have you gone back in 20 years' time to see?
Not really.
Yeah.
Yeah.
Bob,
And
if you
is this
click,
the question of stitching this your system of basically, are you just using mortar to reshape the along the grooves which you make in the longitudinal and transverse direction, and you put the bars, and then you just mortar in, or what?
No. We well, the Marflex is coloured to match the brickwork or the stonework or whatever we're putting it in. We are looking at ways of because a lot of
how do you repointing? Are you repointing with a mortar or what?
No, we just leave the Marflex. Most clients prefer just to look at the Marflex material as it is. We are looking at ways of repointing, but it's always because we need the lever arm in the barrel, so we need to have our bars as near the surface as possible to give us the maximum lever arm for the strength. And we are looking at ways of maybe repointing with some sort of epoxy mortar, but that's as additional expense, and most clients, they're very happy with the Mars system as it is.
Without repointing, how do you provide the bond between the existing barrel and the Mars system?
Yeah, well, that's it. We either have to do it while the Marflex is still wet, or we have been looking at an epoxy mortar, just experimenting with it, just to see the effect, because it would only be about 2 millimeters thick, and that would just drop out if we just use normal mortar.
Bob, if you click on your chat icon, you'll see a number of questions.
If it's easier, guys, I know there's a few guys with their hands up here, so Wayne, I know you had a few questions. Do you want to ask your questions first?
Is that okay?
Go for
can
it.
you hear me okay? Can you hear me? Yeah.
I can hear you.
Okay, brilliant. I have issues with this headset sometimes. Okay, it was a couple of questions. With the adhesive that you use, I was wondering, it obviously serves two purposes. As an adhesive, but it's also to provide protection to the reinforcement as well. What's the design life for the adhesive?
Got a feeling Bob might have just accidentally gone off the chat. So, Brian, I don't know if you want to answer that one just while Bob probably loads back in.
It was designed. It was manufactured and developed for us by a company called Newfins, which are part of the USL group, and it was based on materials that they've used in expansion joints that have been around for about 90 years now. So based on that, we've no reason to believe it would give any lesser life than the 120 years that Bob has already spoken about. Certainly, there's been no distress or deterioration in bridges that have now had the Marflex installed for 28 years.
That's brilliant. Thank you. That's really impressive. It's now 120 years.
I think. Am I
yeah.
back? No.
Yeah, you're back. No, Bob.
Good.
I think Brian's answered that question. So I'll just move on to the other one if that's okay, quite quickly. So in terms of the failure mechanism, you know, the 4-hinge failure mechanism is what you're trying to prevent here. By introducing the Mars system, how will it change the failure mechanism? Is it still ductile? And something that stood out to me as well is that inspecting bridges is quite reassuring in a way when you do see cracks forming, because it is a sort of a ductile failure mechanism that you're witnessing. If we're now stitching that effectively or introducing reinforcement which will perhaps hide that defect forming, is it a possibility that cracking in the hogging part of the arch, so cracking in the extradors, is taking place and we're not seeing that happening?
Well, I totally agree with you. It's nice to see cracks, and we don't hide them because our material is flexible, so we allow the movement, the natural movement of the arch that you like to see, and so do I. And the tests that we've done on the Mars system, all the tests that we've done, they've all failed using the 4-hinge mechanism method. I think I did get one with a 5-hinge, but the Mars system is just as effective on 5 hinges as well. But yeah, it's all been, they've all still failed as the 4-hinge mechanism. The software will predict the failure mechanism anyway. So the software predicts if it fails as in say crushing, then the software will pick that up. So
yeah, that's what I was wondering, is that if it still fails in the 4-hinge mechanism, what component goes first? Is it crushing, which will then, I would suggest, is less of a ductile failure than more of a...
Yeah, no, you can only put in so much reinforcement, so you always have a ductile failure.
Okay.
You can't over reinforce the section, so that's really our limit, the thickness of the barrel and the amount of reinforcement that we can put in.
And would that be yielding of the reinforcement or some sort of pull out?
It's yielding of the reinforcement that takes place.
Okay, Brill, thank you.
Just move on to the next question quickly, Bob. I think Nick, you were next in line, so if you want to fire away, Nick.
Yeah, thanks for your talk today, Bob. That's really useful. Really good to hear about it again. I know we have looked at using your systems in the past. We have sort of developed approval in principles based on the systems. I don't know, in the last few years, has there been any new or any additional network rail bridges done with the system? And our biggest issue actually was sort of getting it past those RAM approvals, the buy-in of the system. And it did seem to vary across the country.
Yeah,
sort of where you were.
Yeah, we're doing one at the moment. In Wales, the one that I showed you, and that's a current one. We're actually installing the system as we speak. Yeah. Okay,
great. That's good to know. It's sort of coming in. I mean, the sort of, I suppose the more of these structures you have there, the easier it is for us to sort of say to the network rail guys to say, look, it's been used here. It's been used here. We've got it on the network, sort of thing. That was definitely our difficult issue.
Network rail were the hardest nut to crack, to be honest. I had. I spent because I used to be in a committee with the chief engineer for Network Rail, writing that Syria manual on masonry bridges, and he was very dogmatic and very traditional, but Network Rail seems to be a bit more flexible now.
It's good to hear. Thanks for that.
Thanks, Nick. If we go to Callum.
Yeah. Thanks for that, Bob. Very good presentation. I was just curious to your claim that arch bridges aren't behaving in a 3D manner and that 2D is more reflective. Obviously, 2D is easier to analyze that and present the benefits of the system, but the reality is there must be some 3D transverse distribution behavior going on in the arch, which may be our inability to assess in 3D is why we're getting these theoretically low capacities on arches that look fine and behave fine. one of the loads are subject to? And I just what makes you think they behave in such a 2D manner?
It's really just that normal arch, we invariably, well, say 90% of them, of this crack going down between the spandrels and the barrel, so that's really behaving in 2D, and I think it's dangerous to assume a 3D behavior. But I will accept that some arches, if you don't get that crack around the barrel, and the movement will be in the spandrel walls probably, but arches do have to move backwards and forwards, etc., to carry the load. Always a bit suspicious of 3D behavior. And as you say, it's easier to analyze. So. Yeah.
Thanks, Callum. Next one was a gentleman called Tushy.
Hello, Bob. I remember ASARC when it was the DOS program, but we actually switched over to Arch by Cascade, so it wasn't.
Oh yeah.
But anyway, the question I have is, in one of maybe one or two of your case studies, you said you had theoretical results from your software which closely matched the actual results of the load tests. I mean, they were pretty close. I think 349 as opposed to 345. Was it only in one or two tests that you tested your software, or was it across many examples?
No, well, the actual ASARC was tested against a number of examples. Well, it was independently tested by OVARP, and the MARSYS is just a little extension to the ASARC program, and that actually gave us the right answer for the test at Transport Research Laboratory. I've also applied it to a number of the small arches that we did in the laboratory at the university, and it seemed to work well there, but a 1 meter span is not really a very good basis for validating software. So yeah, it was just really the MARS system, but that's just an extension to, say, the ASARC, and so it was fairly well proven.
I mean, Arch, which was the tool at that time that we used.
We used Arch.
Arch by Cascade rather than Arch.
Oh, Cascade, yeah. Oh,
yep.
Yeah.
So
they copied.
The problem was there were some profiles of Arch that didn't actually match the predicted results from Arch, and I was just wondering whether you found that with ASARC, or is that something engineers now should be looking at? As a tool.
Well, no, ASARC isn't commercially available now, so we're not selling it to you. Just use it in-house, mainly because SSP went sort of bankrupt, went to the wall in the 90s, and that stopped the commercial development of ASARC, if you see what I mean. So we just kept it in-house and used it for the MARS system.
So is that just still a mechanism method? It's based on the mechanism method.
It's more than a mechanism method, sort of equilibrium method as well. It combines the two, just because it looks at the material failure of the arch as well as the mechanism. So it's not just a mechanism analysis, it evaluates material strength and all that sort of thing in the arch.
Just one final question. In one of your case studies, which was the bridge in Sheffield, where you had that stonework, and you strengthened that bridge. What did you do after that? Did you put a concrete saddle, or did you put it backfill?
No, it was a concrete lean mix concrete over the bridge, which I don't think was necessary, but the contractor did. So
right. Would a concrete saddle, since you'd opened it up anyway, would that have been sufficient on its own to?
Probably. I mean, I think concrete's, well, this gets into a whole other subject, but a lot of bridges where you relieve the load on the barrel then loses its compression. So the compression gets relieved within the barrel. And we've seen brick arches. I mean, in this case, it wouldn't been the case, but we've seen brick arches where bottom rings falling out because it's been, say, an old railway bridge and it's been now used as a footbridge, and so the barrel relaxes and the bottom ring becomes less stable, and I could show you slides of ones that we've had to replace a whole bottom ring. We put the mast system in the other rings and put another bottom ring on. So in this, and the bridge in India that we're doing, that's not got much load on it, and the blocks are actually becoming loose because there isn't the compression in the arch barrel. Yeah, I'm always a bit dubious about. I mean, the putting a saddle over is not environmentally friendly, and it uses a lot of concrete, a lot of big plant, and in this case would be unnecessary. So that's, I could put slides on about the argument against using saddling because of the environmental effects. Because the mast system just uses minimum material, and so it's a lot more environmentally friendly.
Thank you very much.
Mm-hmm.
Thanks, Toshi. I think that there might be one or two more in the chat. I'm just conscious of time, people trying to get away. But I know, Adil, you had your hand up.
Sorry, no more chances to ask any more questions. Yeah, just wanted to know, is the reinforcement you are specifying, is it stainless steel or just normal reinforcement?
Stainless steel.
Stainless steel, okay. And second thing, when the situation, when you have a crack between the spandrel and the bar, do you think we still need to have a stitch first, isn't it?
No, I think definitely not stitch that because you need that to move. So you still need the flexibility in that crack because you want the barrel to move slightly differently to the spandrel walls. So I think you still need movement in there, and that's what our bars do because it's in the Marflex and it still allows that to move.
The bar in the soffit wouldn't be an effective to, isn't it?
Yeah, I mean it holds the spandrel walls in, but we still allow the movement between the spandrel wall and the barrel.
Thank you. Thank you very much.
Thanks, Adil. I think there was a few more in the chat, but what I'll do, Bob, I'll kind of forward those over to you, and then we can go back to those via email. Just kind of conscious of time now, but yeah, everyone else, I think we've got through everyone who's had their hands up. So thank you for asking Bob those questions, guys. Thank you all for listening.
Thank you.
Thank you very much.
Thank you.
Thanks.
Sorry for leaving when the questions were coming.
Thanks.
Sorry, would you mind if you provide us the presentation slide, or is that possible?
I can't provide the slides. Matt's recording the presentation, so we could make that available.
Yeah, we can do the recording. We can share the recording of this session, so you can go back through if that's easier.
Could you make it as a YouTube video?
We could do, yeah. We can put it on there, and we can just share the link so people can go through there at their own leisure. That's not a problem. So if you do want a video, just drop a line in the chat or to me, and I can make that happen. And then hopefully see some of you guys or most of you guys on the second part in a few weeks in June.
Will that be an automatic invite? Will it?
Yeah. So you guys who have signed up here, I will send another one out for part 2, so you can attend that. It'd just be a case of accepting the invite via Teams again and logging in as you have done today.
Thank you very much.
No problem.
Thank you.
No problem. Thank you, guys.
Thanks again.
Yeah.
Cheers.
Thank you.
Bye.
Bye.
Thank you. Bye.
Bye.
Thank you.